Chapter 4, of course, is quadratic functions and factoring. And in particular, we're going to be looking at the use of the quadratic formula. We want to get to the place where you understand when you need to use the quadratic formula and how you use it. Now, I want to ask you a question about these balls of the juggler that we're looking at. In class, we actually looked at a video of this amazing juggler that was able to manipulate the balls in so many different ways. But in this question, thinking of this picture and keeping it in mind, what parts of a quadratic function would help us determine the height of a juggler's ball? What aspect of the quadratic function, speaking mathematically, is the actual height? And then what part of the quadratic function would help us determine the time that the ball is in the air? These are the types of questions that I'm going to ask you to think about and to consider and to answer when we get to the end of this section. So first of all, I want to take a look at a situation where we come across a quadratic equation that will not factor using the tricks that we have. Something like this. If you think about it and look at it, what multiplies to be 3 and adds to be -5? Problem is, when we really stop to consider it, there is no possibility of factoring that we can use. So instead, we have to use something called the quadratic formula. The quadratic formula is the following formula. It's based on the general version of the quadratic equation where a is the coefficient with x squared, and b is the coefficient with x, and c is a constant that is just there in the equation. And here is our formula. Now, some people remember this by singing. They use Pop Goes the Weasel. So if you'll forgive my gravelly voice, it would sound something like this. X equals -b plus or minus the square root of b squared minus 4ac all over 2a. We'll be practicing that in class so that you can get a chance to memorize it in that way. But it applies for a question like this one. So we're going to take the B from here, the A from the front, and the C, and plop them in place. Now, there is the question one more time. Here it is where I put the numbers in place. Simplifying, a negative turns into the positive. -5 squared is 25. These guys multiplied is 12. And so I get the following answer. Now, this literally gives me still 2 zeros for this quadratic equation. So I use my calculator. 5 plus the square root of 13 divided by 2 gives me one answer, and 5 minus the square root of 13 divided by 2 gives me the second. Now, when you work with the quadratic formula, you have to be prepared to handle what we call radicals and ultimately complex numbers. Now, we're going to do complex numbers in the next section, but today we're just going to review the rules of working with radicals. Radicals are any number that actually have a square root sign, or a root sign, we often call it. Things like these. So we're going to go through some questions like these, and I'll go through the process trying to explain how we simplify these things. Okay, the square root of 80, what we're looking for are perfect squares inside of 80. Now, the first thing that comes to my mind is 80 is equal to 8 times 10. Now, neither one of those guys are perfect squares, of course, but there is a perfect square if I take 4, because this is 4 times 2. And since this guy is 2 times 5, I could say that it's 4 times 4 times 5. Here is a perfect square. And so when I take it outside, the square root of essentially 16 is 4, and the remaining part of the number stays within the radical, and that is a 5. If I have two radicals that are multiplied together, as long as they are both the same square root, then I can put them together, so it's 126. And again, I'm going to look for numbers that have perfect squares, 9 being one of them, so 9 times 14. The square root of 9 is 3. So my final simplified radical is 3 root 14. Here's something which is a division, basically, within a square root sign. So, easy enough, square root of 4 is 2, the square root of 81 is 9. And so our answer is positive and negative 2 over 9. Well, the next one, it is going to be that we have the square root of 7 on top, but the square root of 16, thankfully, is a 4. And so our answer is a combination, square root on top, and the denominator is a whole number. That's perfectly acceptable. In this one, however, because I can neither reduce the 5 nor the 2, it's going to leave me with a square root in the denominator, and I'm not allowed to keep it that way. And so the easiest way to get rid of it is to multiply it by itself. So I'm going to multiply it by the square root of 2. Over the square root of 2 is essentially a 1. And so while I'm going to change the way the question looks, I'm not harming it in any way. And so we will get the square root of 10 over the square root of 4, and the square root of 4 is 2. Okay, here you have a question once again. It did not have this part to it when it was written originally, and so it's just this one. What do I do when I have something like 7 plus the root of 2 underneath? The trick for this one is using something we call the complex conjugate. And that means I'm going to use the same thing as 7 plus the square root of 2, except I'm going to use a negative sign. And what happens with this one is that this is essentially the difference of squares. And so when I multiply it out, it's going to be 7 squared minus this thing squared, which is essentially a 2. So down the denominator, it simplifies to 47. Up top, we are distributing, so 21 minus 3 root 2. And there you have your answer. Whoops, sorry. Now, one other aspect of the quadratic formula that we can use is that we already know that it's useful for solving quadratic equations that won't factor. But beyond that, when we think of how it works in terms of the zeros, possible zeros you can have, we can have 3 different scenarios. You can have one x-intercept, so where the quadratic sits on the x-axis. You can have none. And you can have some, and there are millions, of course, where it goes through and touches that x-axis 2 times. Now, a fast way to decide what your answer is going to look like is to use something that we call the discriminant. It's a part of the formula which helps us discriminate what the answer is going to look like. So when you look at this quadratic formula, it's right under here. This phrase, b squared minus 4ac, is the one that's going to indicate if it has a real root or not. If this turns out to be a negative, then it has to be imaginary. If it turns out to be 0, you would only have one answer. If it turns out to be something positive, then you're going to have this one plus that number and this one minus it, so you end up with 2 real roots. This is what we call the discriminant. So once again, when this part is a 0, I have only one real intercept. When it is positive, I can have 2. And when it has negative, it has, when it's less than 0, the discriminant is less than 0, then it is imaginary and does not exist. Okay, so use the following equation and see if you can evaluate the discriminant for it. So all we do is take out b squared minus 4ac, and we take the numbers out, and we get a number like 36. Well, if I had 36 under there, I could add it and subtract it, so it would have 2 real solutions. Here's another one. Once again, when I take out the a, the b, and the c, and I calculate the discriminant, I get a negative number, which means it would be a negative under a square root, so it's not going to have any real roots. So lastly, we're going to look at some real-life applications of this kind of stuff once again. So back to our juggler. A juggler tosses a ball into the air and catches it again. How long is the ball in the air if the motion of the ball is represented by the following equation, where x, this guy, represents time and f of x represents the height? Well, in passing through that one, we're going to have to try and find the time it takes. And so we're going to use the x-intercepts. And as we look through the x-intercepts and do the quadratic formula, thank goodness we have a calculator, we get 2 possible numbers. Now, let's go back to the question again. How long is the ball in the air? Okay. And f is, okay, good. How long is it in the air? And so there we have it. We've got 2 possible numbers, but there's no such thing as negative time. And so 2.52 seconds sounds great. All right, there you have it. Solving quadratic equations using the quadratic formula. Have a great day and make sure you bring your questions to class if you have any.